So it's going to have the horsepower kilowatts. It's going to have the number of frames, and the number of phases. It's going to indicate the type of frame the motor has. It's going to give us the volts at the frequency. It's going to give us the volts that the motor is designed to run at. It's going to give us the full load current of the amp. It's going to give us a code that indicates the amount of current the motor should pull when it's starting, or we call it block motor. It's going to give it the service the service factor. It's going to give us the class of insulation, the ambient temperature, and something called the temperature dial. New ones are also going to give us efficiency, and they're going to tell us what size. So what happens is we got the formula for inductive reactance. So X of L is equal to 2 pi FL. Everybody, you don't need to know that. The capacitor, the capacitor is 1 over 2 pi FC. In AC, you'll learn about Eli the Iceman. And what it's saying is that in a parallel circuit, okay, this is constant. The current lags in an inductive circuit, and current leads in a capacitor. So what you find out is that capacitors and inductors are exactly opposite of each other. And if we put them in the circuit at the same time, depending on how we arrange them, they will cancel each other out. So I mean, I've got an inductor that creates a lagging phase shift, which means the current is lagging. And I can put a capacitor in there in parallel with it, which creates a leading, and I size them right for 60 hertz. They will literally cancel each other out. So the new motors, because we have two types of power in an AC circuit. What's the two types of power? We have real power, also referred to as true power. And then we also have apparent power. So apparent power is how much we pay for. Real power, true power, is how much work we get. And in an AC circuit, what we would like, and the ratio between these two, power true or real over power apparent, this gives us something we call a power factor. And what we're shooting for is we're shooting for a power factor of 1, which means there's no all your true power and your apparent power equal to. So now we're paying for the true work we get. Well, the problem is in AC, we have this garbage right here. So motors are predominantly inductive. So they try to create a lagging power factor. If they can give us some type of indication of what type of capacitor I can add in parallel with that thing, then we can get the power factor up to 100% or 1. Okay. So there's actually another measurement, and I think that's in this thing right here. So horsepower, the measure of power, originally used to compare the output of a steam engine with the power of a draft motor. So they had a 550-pound weight, and they try to see how far they could move that in a minute. Or well, actually, they would do it like in 5 minutes or whatever, and then they would calculate what they called it. So this is basically the amount of work. So it'd be 550 foot-pounds per minute. Varies between geographical locations. Most countries now use what we call the standard unit or the international standard of the watt, and we already know it's what, 476 watts per horsepower. Okay, in the U.S. Over in Europe, the formula is a little different. Are we okay? So this is the conversion factor. Normally motors are rated in kilowatts. So we could take horsepower and then we could multiply it by 746 and divide that by 1,000 and that would give us a kilowatt. Or we could go ahead and take the 746 and divide it by 1,000 and get the same answer. But our answer is going to be in kilowatts, right? You understand that? Yes or no? So the actual formula we would do is we would say horsepower times 746 divided by 1,000, and then our answer would be in what? Kilowatts. Or the way the formula says, most of the formula says horsepower times 0.746. So what did they do? They went ahead and divided the horsepower times 1,000. Yeah. And then we can go from kilowatts down to back to horsepower by taking the number of kilowatts the motor is rated in and divide it by 0.746, which it is sometimes. And that would take out dividing by 1,000 and multiplying by 1,000 out of the formula, right? So most of the books you look at, these are the two formulas they give you to go from horsepower to kilowatts and kilowatts to horsepower. And why would you need to know this? Overseas, yeah. So if you go down here to Mercedes, right, you understand, their motors and everything predominantly come from overseas, right, you understand. They probably use a lot of Siemens equipment down there. And so their motors are going to be rated in kilowatts. And you've been taught horsepower all your life. You know, you're trying to figure that out. So these formulas are readily available on the internet. So a frame code gives the physical dimensions of the motor frame and shaft. NEMA, what does NEMA stand for? We've already talked about it a couple times in this
National
Electrical Manufacturers Association. So these guys, some of the things, they do a lot of the physical characteristics of electrical components. So one of the things that they took upon themselves is to set up NEMA frame numbers. So most of your motors now is going to have a frame number in it, which would tell you how it mounts, the spacing between the mounts, the length of the shafts, the size of everything would be specified in one letter, and you would look that up on a chart. This is the motor frame handout. This is up in the motor spec station if you wanted to go look at it. We're not going to go up there. So that's one thing, if you're going to buy a motor, you don't have to buy the motor from the manufacturer, right? You just got to get it with the same electrical characteristics and then the same mechanical characteristics. And you can replace that motor from anybody. A lot of people don't understand that. So just about everything about a motor is a NEMA standard. So it's going to have a code letter on there. It's going to have a letter up there. Everybody should understand this. Both phase, amps, and service factor, the voltage rating of the motor, the number of electrical phases, 1 or 3, right? Amps or full load current, the current the motor draws when running at its rated frequency at its rated voltage under its rated load. This rating also assumes the phase voltages are balanced. So if you got a 3-phase motor, that means if it's 240 volts, then all 3 phases better be what? 240 volts. So we assume that all the phases are balanced. And this don't happen. This doesn't happen sometimes in industry, where they put more load on one phase than they do on the other. So this is why when we hooked up our transformers, I wanted y'all to rotate, right? Some of y'all use phase 1 and 2, some of you use phase 2 and 3, some of you use 1 and 3, and that way we try to keep our phases balanced. So if we went over there and measured those 3 voltages from phase to phase, they should all measure the same. If they don't, that means my motor might do a little thing different on one phase or pull a little more current on one phase than it does on another phase. So this all depends on balance. Service factor, this is a multiplier used to calculate how much the motor can be safely overloaded over a short period of time. So if it's got a service factor of 1, like our motor does over there, it's got a service factor of 1, what does that mean? We can't overload that motor. We can't plug that motor either. What's plugging? When we plug a motor, what's plugging? Reversing it without it coming to a stop. We're course, that means that sucker's going to pull a ton of current, right? You understand? A lot of times it'll kick an overload because it depends on what it's got to reverse. And a lot of times it takes longer to reverse than the overload is set to handle. You'll see that people do it, but you can do that on an attic fan. You go over and flip it from forward to reverse, you can hear that sucker hum real loud because it's pulling more, pulling a lot of current. Wake up, Maurice. Maurice. Okay, Gracie. If you're going to sleep, guy, go out in your car and go to sleep. Don't sleep in class, okay? So here's our start current code. So we got a code on there that indicates our start current. It's only a 1-letter code. And it means, okay, if my guys, and we use 6 to 8 as rule of thumb, but that's not true. If you got the code, if you got the nameplate, this is what you would use. So it says if it's got an L on there, then this guy here could pull about 9.5 times. This is the multiplier of what the start current is. Right? Does that make sense? Typically. A minimum of what? 9, a maximum of 9.9. So normally we try to use, and if you got a V on there, those things are not limited. That's the guys that are going to pull like that. Yeah, no limits. So this is the information they provide on the nameplate. Used to, I learned 6 to 8 times, and that's what we use if you don't know that. But now they actually give you a letter that indicates how much this sucker could start if you start it on what we call across the line. So if we come up here and we have a relay that switches this thing across the line, that sucker could pull almost 9.5 more amps than it does just to get it run, just to run it, right? And this is where your reduced voltage starter would run. So if you had a reduced voltage starter, you put resistors in series, or sometimes they use SCRs or triacs. They do it electronically, and we reduce the voltage to the motor, and then the motor doesn't create all that torque, and it won't pull all that starting current. So this is very, very popular in big motors. Then we have an ambient temperature. This is the temperature. So first of all, we have what we call the motor when it's not running. And this is called the ambient temperature, which is what? 40 degrees, which is about 140 degrees Fahrenheit. So every motor I've ever seen has got ambient temperature has got 40 degrees centigrade. And then we have an insulation class on there. This is what the insulation is rated at above the ambient temperature. So what we mean is this guy right here could run up to what? If you got a class 8, it could run up to 180 inside the motor while it's running without damaging the insulation. Everybody okay? Above 40. That's pretty hot, ain't it? And that's sun dry. Boiling is what? 100 degrees, right? Temperature rise by resistance method or a medium induction motor. So this is just something else out here. So if it's got a service factor of 1 and it's got an A on there, then it can have a temperature rise up to what? This is ambient temperature up to 60 degrees, right? If it's got a B rating, it could be up to 80 degrees. An F rating, it could be up to 105 degrees. And an H rating, it could be 120 degrees. With a service factor of 1, if it's got a service factor of 1.15, then notice we can run it hotter, right? Totally enclosed. What do we have? So we have motors that are totally enclosed. The problem with totally enclosed motors is there's no ventilation within the motor. And we use these, I've seen them sealed up, I've seen them run underwater. Totally enclosed motors run underwater. These are going to be used in very, very harsh environments, or very environments where we don't want electrical sparks or anything to get into the system. Motors with encapsulated windings, and this is very, very popular on motors because those windings try to vibrate all the time because they got AC on them, right? You understand that? And this is why transformers hum and motors, AC motors hum. Well, the problem is that when this is the north, this is the south, right? You understand? And the motors will the windings have a tendency to come together. And then when they go to 0, they would have a tendency to spring apart. So that's why transformers wind. And so if you got that very thin insulation on there, and if it keeps touching a lot like that, it could eventually short some windings out. So a lot of times they'll take that stator and they'll dip it down inside a lacquer or varnish type thing to keep those windings from doing what? From vibrating. A lot of transformers do that. So this is just temperature rise. This could be on the motor. Well, what else could be on there? So there's this is up on Blackboard, by the way. So that this is just basically on a standard motor, but what they've done is they're giving us a lot of information, a lot more information than they used to give us on this thing. And this is up on Blackboard, by the way. And what would this be at?
Course content.
No, this is just.
Oh, for the handout. Oh,
And we got general information, electrical formulas, thermocouples, motor specs, and this is what you're going to use for. This is the actual nameplate on our motor. Oh, no, it's not. Oh. So this is the nameplate on our motor. So here's the frame number. So I could go into that. Let me blow this up for y'all. So here's the frame number. So we could go into that chart and look up frame HA.56C, and that would tell us the spacing between the mounting holes on it, the mounting plate, how high it sets up, the length of the shaft, and all that other neat stuff. This tells us that this is a how many horsepower motor? Half horsepower, runs at 1725. It's a 2-pole motor. Sorry, 4-pole motor. At what? 60 hertz. It's what? 3-phase. Service factor of 1. I mean, we can't overload this motor, right? It's not designed over. So we definitely can't flood it. We're going to run ours on 208, 230. We can run it on 208, 230, or 460. This is the full load current. If I run it on 208, it's going to pull 1.6 amps. If I run it on 230, it's going to pull what? 1.8 amps. If I run it on 460, it's going to pull 900 milliamps. Okay. This wasn't on there. This is what we call it. We got two types of motor. We got what we call intermediate duty motors, and we have continuous duty motors. A continuous duty motor means it's designed to run what? 24 hours a day, 7 days a week, 24/7. An intermediate duty motor would be able to run in short bursts. So a lot of compressors use intermediate motors. This is 40 degrees. It's got insulation class what? See, this is the type enclosure. We can look up on that. This is the code right here, code M. What would that mean? So this motor could pull almost 11 times its starting current. When we started under load, not when we're going to do it, because we're going to run these motors unloaded, right? So if I was to start that thing under load, right, you understand that, this guy could pull up to what? Well, it actually could pull up to what? So we use a rule of thumb of 6 to 8, but it actually is going to vary depending on the code of the motor, right? Everybody understand that?
so Mr. Reed, if imagine if someone has a V on it that says no limits, or how you are that?
I guess you would measure it. That's the only thing I can think of. It just means it has no limit.
That's what I'm saying. You say no limit.
I've never seen a B-rated motor. I can imagine that's what you would do. It all depends on the application, but it's going to pull a lot of current when you start it. So odds are that motor, you will deliberately limit the voltage to the motor to start that motor up. That's all I can say. So that's all the information that we need, right? You understand that? And also, I need to, what I didn't get off the nameplate is how to wire it for either low voltage or high voltage. That's on our nameplate too. So that was on the motor. But ours is a 9-lead motor. And so we've already looked at how to light it. So we wire them in series if we're doing high voltage. We wire them in parallel if we're going to do low voltage. But you don't even have to know that because it's going to have a plate on there that says what? High voltage, and it says low voltage. So we're going to run ours on 208. So which one of these would be high voltage? If I run it on what? 460. So it means we're going to wire ours for low voltage. I'll look at the nameplate. I'll look at where it says low voltage, and I'll pick it up accordingly. Right? Everybody okay? That makes sense. So there is a lab in your lab book called a motor nameplate. What lab number is that? It's a homework lab. It's on y'all's lab sheet though.